Hello again, physics friends. Today we're going to be talking about a very famous problem in relativity known as the twin paradox. And of course, like all of the paradoxes we've talked about so far, once you take into account everything, there is no paradox at all. But here's the apparent paradox that we have to resolve. We're going to have the following setup. We have Bob on the Earth, and we have Alice in her rocket. And Alice is going to take a trip from the Earth to the nearby star Sirius, which is 8 light years away. Okay. And if we look at the situation from Bob's point of view, I forgot to tell you, Bob and Alice are twins, so they start out at the same age. They're born on the same day. They're currently the same age. Now Alice is going to travel at relativistic speeds from the Earth to Sirius and back. And from Bob's point of view, Bob says, okay, well, I know something about relativity, and I know that Alice in my frame is a moving clock, and so her clock will tick less than my clock. So when she comes home, when she returns back to Earth after her round trip, she will have aged less than me. So for example, if Bob would say if Bob ages 20 years, Alice will be less than 20 years older. And so when the twins come back together and they reunite, Bob will be older than Alice, even though they're actually twins. Okay? So that's fine. That seems like a reasonable way to approach this. Let's see what Alice would say. So in Alice's point of view, Alice said, well, I'm at rest, and it's Bob that departs me, and then when Sirius arrives at me, then Sirius will now depart me and go the other direction, and Bob will return to me. So it's Bob actually that takes the trip, not me. I'm always at rest in my own frame. And since my clock is at rest and Bob's is moving, his clock ticks less than mine, so that when we come back together, he will be the younger twin and I will be the older twin. Okay, but we can't have it both ways, right? If Alice and Bob start out the same age and then they depart each other, when they come back together, one of the two is going to be older and have more wrinkles than the other one. They can't, once they come back together, they can't simultaneously be older than each other and younger than each other. So one of these analyses is correct, and one of them has a flaw in it. So let's see what the resolution is and what we're gonna see. It's a bit of a subtle problem, but the key idea here is that the rules of relativity apply in an inertial frame, a frame that's moving at a constant speed in a straight line, or is at rest in a given frame. Okay, so in Bob's analysis, Bob is in this rest frame that's not moving relative to the Earth, and he's watching Alice take this trip out and back. And his frame is definitely a valid inertial frame, right? He's at rest. That's definitely an inertial frame. And so there seems to be no problem with that analysis. Alice's frame of reference, on the other hand, is one that moves at a constant speed in a straight line for the outbound trip and a constant speed in a straight line for the return trip. But those are two different reference frames, right? The first reference frame is one, her reference frame is always at rest, but in Bob's point of view, Alice is moving to the right, and then she's moving back to the left. So she has changed direction, and in order to change direction, you must slow down, stop, turn around, and speed up. So that corresponds to an acceleration, and Alice is therefore not an inertial frame. She is an accelerated frame, even though for most of the trip she's moving at constant velocity, and then for the return trip she's also moving at constant velocity, but a different direction. So these are representing two different reference frames, and because Alice is now changing her frame, that corresponds to an acceleration. Okay, so we'll get into the details about acceleration and how to handle that in a minute, actually in the next video. But in this video, let's work through the problem with numbers, just so we get kind of a sense for how this problem goes. And so we'll put some specific numbers on this problem. Now we'll dress up this diagram. Let's say that the Earth and Sirius are 8 light years apart. So we can represent that distance in the following way. And we're going to say that when Alice departs Bob, their clocks are synchronized and set to 0. Okay, so this is an analysis in the Earth frame. And if you like, we could call it the Earth/Bob frame, because the Earth and Bob are in the same frame. And in that frame, Alice is moving. Now, Sirius, which is a star, we could indicate that by some little shiny rays of light coming off of it. Sirius is also at rest in this frame, as is Bob and the Earth. So its clock and the Earth clock are in sync and will read the same number. Okay, so we can put a 0 on Sirius's clock too. So there's going to be 4 different relevant, significant events here. One is Alice departs Earth, the other is Alice arrives Sirius, then Alice departs Sirius, and Alice arrives back at Earth. So we're going to have 4 snapshot diagrams. I've drawn the first. I'll now draw the next one and then dress it up. Okay, we see now that Bob is still on the Earth and Alice has now arrived at Sirius, and what we'd like to do is put readings on these 3 clocks. Okay, so we'll just use this simple equation, elapsed time is distance traveled divided by speed, and here the distance traveled is the full 8 light years, and the speed is 4/5 c. We have a cancellation of the c's. 8/4 is 2, 2 times 5 is 10, so we have 10 years elapsed in the Earth frame. Those Earth clocks started at 0, and if we add 10 to that, we end up at 10. And remember, the Earth clock and Sirius's clock have the same reading. But then how about the reading on Alice's clock, right? So there we have to worry about time dilation, because delta t Alice, which is the moving clock, is equal to delta t Earth, or delta t Bob rather, divided by gamma. Delta t Bob was 10 years. That's the time ticked off on a clock at rest, or also called the elapsed time. And here gamma, for v of 4/5 c, that corresponds to a gamma of 5/3. So we got to put gamma of 5/3 under the 10 years. 10/5 is 2, 2 times 3 is 6 years. So her clock has only ticked off 6 years. So this is what Bob says this is what Bob means when he says that Bob is older than Alice. He's saying she's traveling, her clock ticks less, therefore she's only aged 6 years, and I have aged 10. Okay, so we're done with half of the problem, and now we need to allow Alice to turn around and come home. So the next 2 diagrams correspond to the return trip. The first is Alice departs Sirius, and the second is Alice arrives back at Earth. So let me draw those. Okay, so here we have the situation. Bob is still on the Earth. Alice is still at the location of Sirius, but now her rocket ship is facing the other direction, ready to come home. And in order for her to make that turn, right, from moving to the right to moving to the left, she will have to slow down, turn around, and speed up to get to 4/5 c. And that will take some time. But let's assume that it takes, let's say, 1 week to slow down and 1 week to speed up. Here we're talking about years of travel time. Okay, so the time it takes her to slow down, turn around, and speed up is very small compared to the one-way travel time of 10 years in Bob's frame, or 6 ticks of Alice's year clock. So essentially, no time has elapsed, and we're going to make that idealization that the reading on the clock on Sirius still reads 10 even after the turnaround. Now, if you'd like, you could write this as 10.0 with the understanding that even if it takes a week to slow down, turn around, and speed up again, that reading on the clock might have advanced a tiny bit, but it's still at 10.0. And if that's true, then the Earth clock also reads 10, and Alice's clock still reads 6. Okay, so again, the idealization here is she can change her speed essentially instantaneously compared to all other time scales in this problem. Okay, so Bob is still only 10 years older than he was, and Alice is now still 6 years older than she was when she left. So next up, we're going to draw the final diagram in the series, and that is that Alice arrives back at Earth. Okay. So here we have it. And the final item that I want to do is put numbers in these three clocks. Well, the distance for the return trip is exactly the same as it was for the outgoing trip, right? It's still 8 light years. The speed of Alice is the same for the return trip, 4/5 c. And so it's going to take the same amount of elapsed time for her to make the return trip as it did for her to make the outgoing trip. So Bob's clock is once again going to advance 10 more years. So he's going to be at 20 years, same for Sirius. And Alice is going to tick off 6 more years. So her clock rises from 6 to 12. So Bob ages 20 years, Alice only ages 12 years. So now, although they started out as twins, Bob is older than Alice. And so we like to say that time travel is in fact possible, but you can only travel into the future. You can't travel into the past. So by taking this trip, Alice has kind of traveled into Bob's future. He is now 8 years older than she is, even though when she left, they were the same age. So this is the twin paradox as viewed from the Earth frame / Bob's frame. Let's see what the situation looks like in Alice's frame, which we'll call the rocket frame. And there's 4 differences that we need to pay attention to when we do the analysis in this frame. The first is that instead of Alice moving to the right for the outgoing trip, Alice is at rest and Earth and Sirius move to the left, okay? Number 2, Earth and Sirius are not 8 light years apart. They are closer than that together because of length contraction. Number 3, clocks on the Earth and on Sirius are not in sync in this frame because those clocks are moving. So we have to account for the rear clock ahead. And number 4, the Earth and Sirius clocks are moving, and so they tick less due to time dilation than Alice's clock, which is at rest. So those are the 4 things we have to keep an eye on. But once again, we're going to draw 4 snapshot diagrams representing the 4 relevant events in this problem. Okay, so here we have the Earth and Sirius. So we got Earth and Sirius here. And we'll decorate Sirius with rays of light. And I've drawn Earth and Sirius as less than 8 light years apart because of length contraction. In fact, Earth and Sirius are only about exactly 4.8 light years apart. I've also chosen to draw the Earth and Sirius not as circles, but as kind of ovals because the objects themselves are contracted in their direction of motion, so this circle becomes an oval. That's not critical for this problem, but it is another visual reminder that these objects are moving. And of course, we indicate their motion also directly with a velocity vector arrow. It's still the case that the reading on the Earth clock and the reading on Alice's clock are 0. Those are set to be 0 at the instant that Earth departs Alice. That's still going to be true. But now we have the fact that the clock on Sirius does not read 0. It's set ahead by L naught V over C squared, which is 8 light years times the velocity of 4/5 c, or the speed of 4/5 c, divided by c squared. So all of the c's cancel, and I get 32 fifths. 32 fifths year is 6.4 years. So in here I can put 6.4 as the reading on Sirius's clock. Okay, the next diagram will be Sirius arriving at Alice. So let's take a look at that. So we can then ask, how long does it take? How much time has elapsed in this frame, in Alice's frame, between these 2 diagrams? And the key idea here is that Sirius has to travel 4.8 years in order to arrive at Alice. And we know that Sirius is traveling at a speed of 4/5 c. So we can say Sirius travels 4.8 light years at a speed of 4/5 c. So that takes an elapsed time of equal to the distance, 4.8 years c, divided by the speed of 4/5 c, and that corresponds to 6 years. Okay, so we know that Alice's clock reads 6 at this instant, which we knew from the last analysis, that when Sirius aligns with Alice, her clock reads 6. Okay, so that is the elapsed time. How about the time ticked off on the moving clock? So Sirius and Earth's clock. Well, here we have to account for time dilation because those are moving clocks. So delta t moving equals delta t at rest divided by gamma. In this case, delta t at rest is 6 years, and gamma is 5/3. So that is 18/5, or 3.6 years. Okay. So each of these two moving clocks has advanced by 3.6 years. Well, the Earth clock started at 0, so now it reads 3.6. Sirius's clock did not start at 0, it started at 6.4. If I add 3.6 to 6.4, I end up at 10. So once again, when Sirius aligns with Alice, as in the previous analysis from Bob's frame, Sirius's clock reads 10, and Alice's clock reads 6. Okay, so Alice again would say, in my frame, I have aged 6 years, but Bob, my pal, has only aged 3.6 years because he is moving and therefore he ages less. So far everything seems fine. Alice is correct in saying that Bob ages less than she does. Okay, so now Bob is younger than Alice, and Alice is the older twin. Let's see, though, what happens when Alice turns around. Okay, so the next diagram is going to be really important one. Let's take a look at that. Okay, here we go. For the event Sirius departs, we notice a couple things. Number one, now Sirius and the Earth are moving to the right, and Alice is facing in the other direction than she used to be. She's now facing towards Earth rather than facing towards Sirius. So the most important piece here is that Alice is in a new inertial frame. She has changed frames. Okay, so Alice is in a new frame. Inertial reference frame. And in particular, the rear clock used to be Sirius, right? Sirius was the rear clock and it was set ahead of the Earth clock. But now look, the Earth is the rear clock and is going to read a larger number than Sirius. So when we start populating these readings, these clocks with numbers, the Earth clock is going to change, right? So we're assuming again that this turnaround happens very abruptly so that no time advances on Alice's clock. But if no time advances on Alice's clock, that means the Sirius clock must also read 10, because we know that when Sirius departs Alice or when Alice departs Sirius, the readings on those two clocks are 6 and 10. So that must still be true. Okay. But if Sirius reads 10, now we know that the Earth clock has got to be bigger than 10 by the RCA amount of 6.4 years. Okay. So what that tells us is that the clock on the Earth reads 16.4. So by changing the inertial reference frame, Alice has made Bob's clock jump. And it jumps by 2 times the RCA. In other words, it has jumped by 12.8 years. Right? It started at 3.6 and now it reads 16.4. That's a jump of 12.8. Okay, so that's where the change comes in, because up until this point, Alice says, I'm the clock at rest, Bob is moving, therefore he is aged less than I have. But now, just by changing inertial reference frames, that story no longer holds because she has still only aged 6 years, but Bob's clock has ticked 16.4 years. Okay. So in fact, Bob will be the older twin when she returns back to Earth. So this is the crux of the problem. When she changes her inertial frames, that has an impact on the reading on other clocks. Okay. So to complete this, though, let's draw the final picture, which is when Earth arrives at Alice. Let's take a look at that diagram. Okay, and again, here's our diagram. Earth has arrived. Sirius is long gone. And we want to put numbers on these clocks. Well, we know that the outbound, I guess the time it takes for Sirius to arrive to Alice is 6 years of elapsed time. And that's when Sirius has to travel 4.8 light years. Well, here the Earth has to also travel 4.8 light years in order to arrive at Alice, and it's traveling the same speed, 4.45 c. So it's also going to take 6 years of elapsed time for that to happen. So her clock started at 6. It's going to tick off 6 more years. So in this diagram, her clock will read 12. Okay. And when her clock ticks off 12, the moving clocks tick off 3.6. We saw that before. And so if we add 3.6 to 16.4, we're going to get 20. So Bob's clock is reading 20. And the sun's clock is going to advance from 10 to 13.6. Okay, and so now we have all of the readings on all of the clocks, and the apparent paradox, the paradox has been resolved. Whether we do this analysis in Bob's frame or in Alice's frame, we agree that Alice has aged 12 years and Bob has aged 20 years. So no matter what frame you do your analysis in, we would agree that Bob is the older of the two kids now. Bob is the older twin, even though they started out at the same age. And the crux of the problem, right, is that Alice is not in a single inertial frame for the whole trip. She changes inertial frames at the turnaround point with Sirius, and that has an impact in the reading on Bob's clock. But I do want to reinforce the point that throughout almost all of this trip, it is true that Bob's clock ticked slower than Alice's, right? Except for that short period of time in the turnaround, when in that essentially no time elapsed for Alice, and for Bob, 12.8 years ticked off. Now, this might be for you a satisfactory resolution, or it might be very unsatisfactory. It seems weird that in essentially no time for Alice, Bob's clock can suddenly jump by 12.8 years. And this explanation of, oh, well, Alice has changed inertial reference frames, so that's just what happens. Maybe that sits right with you, maybe not. What we're going to do in a subsequent video is dive more into this idea of how acceleration can affect Bob's clock so drastically in such a short amount of time for Alice. And for that, we're going to have to talk a little bit about acceleration, which takes us out of special relativity and into general relativity. So we'll talk about stopping and starting acceleration and how that affects clocks.